Let's look at the concept of control structures and learn about the three basic control structures that we'll use when developing our programs. This is a flowchart. Have you seen a flowchart before? It's unstructured spaghetti code. And when people were first programming, this is how code was written. The problem with spaghetti code was that it was hard for other programmers to come in and read the source code and make modifications. So in the mid-60s, two Italian mathematicians, Bohm and Jacopini, proved actually the structure theorem. And in the structure theorem, they stated that everything you need to write in computer programming can be done with three basic structures. Now, a structure is just the layout of a statement. It's not the statement. There are many more statements than just three. But the layout of statements follows these three formats, and that's all you need: sequence, decision, and loop. Whether you're going to use a sequence or a loop or a decision or a combination of the three depends on what your program needs to do. Here is an example of a sequence structure. The sequence structure is your most basic structure. It does one action after the next. So when you have to do step 1 before you can do step 2, before you can do step 3, for example, you're doing a sequence. To the right, I have a flowchart. And flowcharts are made of symbols. I'm introducing the name of these symbols here. So this is a terminator symbol, looks like an ellipse, and that's normally where you'll have a beginning and an end. So most programs should have a start and an end. A program should not have 5 ends. Only one way to come in and one way to come out. This is one of the principles of structured programming. There's one place you start and one place you end. This symbol here that looks like a rectangle is called a process symbol. Now, to be honest, normally you need to get your input before you do any processing, because how do I know what I'm processing if I don't have the data inputted yet? But in this flowchart, two processes are being done, followed by an input-output symbol. Okay, so your parallelogram means I'm going to input data or output data, followed by another process and a terminal symbol, the end. Here are 3 examples using different formats of a sequence structure. Then to the left, you simply have a list. And you're going to follow this list in order when you wake up in the morning. Okay, this might not be your list sequence, but it's somebody's sequence of what they do when they wake up in the morning. In the middle, you see this block programming language that we will be using called App Inventor. So when the button is clicked, there's a button on this application, and when the user clicks that button, it does a sequence of 2 things. It plays a sound, I think it's a meow sound, because it's hello purr, and then it vibrates. So these programs are written for an Android application or an Android phone, and so it's going to vibrate 500 times, about a half a second. And then to the right is another flowchart for a simple payroll program. So in most simple programs, you decide what is it that I need to know. And for this simple payroll program, I need to know what the pay will be. And then from there, you work backwards. Well, what inputs do I need to calculate the pay? Well, the inputs I need will be hours and rate. From input, how do I get from the inputs to the outputs? And that's your processing step. This is a typical, very simple sequence program. We're going to start. I'm going to ask for the hours and get that input into this variable called hours. And I'm going to get the input to this variable called rate. And this processing step says, take what's on the right-hand side, calculating using the mathematical multiplication symbol, hours times rate. What is that? So if I input 20 for hours and 10 for rate, that's going to be 200. And then put that result into another variable, and we're going to call that pay. So 200 will be stored in the variable pay. Following that, we will output pay. So 200 is output, and that's what we needed to know. The second type of control structure is decision, and you use decisions all the time. will result is a question you ask yourself. First of all, I have to make a decision. I'm asking myself a question. Which of the two do I want to do? So I implied two right there when I said the decision. That's not always true. So I have to make a decision. I'm going to ask myself a true or false question in a program. And if the decision ends up being true, the question I'm asking ends up being true, I'll do one path. Here, if it ends up being true, I'm going to do this path to the left. And if the question I'm asking here ends up being false, I do this path to the right. New symbol, it's called the decision symbol. And as I said, a decision structure is usually implemented with an if statement. So you got if some condition is equal to true, then we're going to do process A. Else, I'm going to do process B. And if means I'm all done. So if I go back to the previous flow chart. So this would be that then part where we're going to do process A. This is going to be that else part where we're going to do process B. Regardless of which one we do, we're going to join those branches back together and continue then in a sequence, in a single flow of logic. Okay? It is also possible that you only want to do one process. If the card needs gas, then get gas and if. So this happens, I want to get gas if this is true. If this is false, I continue to do in whatever I was going to do in the single flow of logic. Okay, so this is what this one process looks like. So this one process I'm going to call single alternative if. You're going to do something if this statement is true, nothing if it's false, and then it comes back together to a single flow. Okay. Here is what we would call pseudocode logic. If, now there's a variable called weather, and there's a literal, I'll put quotes around it, a string literal called raining. So what's the weather outside? Raining. So raining would be input into weather. Does raining equals raining? Then what logic am I going to do? I'm going to wear my rain boots. Okay, so after you're done here in pseudocode and you get to the else, you go ahead and you do whatever statements after that. Go to work, for example. Well, what's the weather like? It's nice and sunny. So if I'm checking, does sunny equal rain? And that's false. So if it's false, you're going to fall into this else part of your if structure and wear sandals. And after you're done this, all the stuff here, you'll again go and rejoin the logic, whether it's raining or whether it is not raining. You're going to do whatever statements come after the end if. The end if terminates that branching and pulls it back together into a single flow of logic. So just to show you our App Inventor, we're going to get to soon. In App Inventor, you have this block for the if statement. This will be your single flow. There's no else part. So if, and you're going to put some test in here, weather equals raining. And what do you want to do? You want to do something, you're going to put whatever you want to do right here if it is raining, for example. Here is we got two possible branches. When we got two possible branches, we're going to call that dual alternative if. Okay? Excuse me for my sloppy writing. So, if some condition is true here, if that's true, we'll do this. But what if that condition is false? Well, then we're going to do that. Okay? So you plug your condition in here in App Inventor, and then you're going to put steps. And you can put more than one step. So if it's raining, and maybe I want to wear my rain boots, get my raincoat on, and grab the umbrella. So that was 3 things we would do in the true part of that if. So here's another example, that simple payroll application that we looked at earlier. So did not calculate for overtime pay. So suppose I was told, no, this application needs to calculate for overtime pay. Now recall what we did earlier. Suppose you worked 45 hours for $10 an hour. Keep it simple. So 45 would be input into that hours, right? And 10 would be input into the rate. and the pay would be $4.50. There's no possibility of any overtime. So the output would be for $4.50. Now let's take a look at the example on the right. We're told, wait a minute, you got to check if they work more than 40 hours, because if they work more than 40 hours, they're supposed to get time and a half. Okay, so we start off the same with the same, maybe even the same input values. What if they work 45 and they get paid $10 an hour? Okay, now we're going to make this check. That should be in lowercase h there. Is hours greater than 40? Well, what's in hours? 45. So I'm really asking myself, is 45 greater than 40? And that is true. So we're going to take this here true branch, and a new variable is coming up. That's called OT pay. And so, well, what are we going to do? We're going to do what's on the right hand side and assign it to this variable OT pay. So what's on the right hand side? Well, we always do parentheses first, correct? So I'm going to calculate hours, 45 minus 40. So this is going to become what? 5, right? So this person gets time and a half for 5 hours. So 5 times 1.5 times 10. Let's see, I think that's 15 times 5, which I believe is 75. So this is going to be 75. That's what that person's getting for working the 5 overtime hours. That's going to be stored in the variable OT pay. So on both of these, we are calculating and outputting pay, as you see. But the pay here is going to be a little bit different, because I'm going to have to grab that calculation from above, 75. Then I'm going to, well, what did they get straight pay for? Well, we know they worked more than 40 hours, or I wouldn't be over here in the true part, correct? So we're only going over here if they worked over 40 hours. So we're going to take 40 times 10. So this will end up being 400. And why did I multiply first, right? I'm going to multiply first before I add, order of operation. So now 400 plus 75, so this pay is going to be 475, and that's what we'll output, 475. Okay, at the end of chapter 6, it says a little bit about testing. Do you think, and what I did was kind of like some testing, because I put in some input values. What if someone worked less than 40 hours? Did I thoroughly test it? Maybe not. Maybe what this said, someone accidentally wrote hours plus rate. Do I know there's an error if I only tested with input data that took me on the true branch? And the answer is no. Okay, so you always need to put enough testing, enough inputs to test both parts of your branch here. Okay, so let's say instead of 45 hours, this person worked 20 hours. Let's say this is plus. Well, that's called a logic error. Okay, someone accidentally, is the program going to run? Yeah, but someone accidentally wrote the wrong statement here. So it's going to test, is hours greater than 40? Well, 20 greater than 40 is a false statement, so it's going to go this way. Okay, and then it's going to say hours, well, that's 20. And rate, that's 10. So I'm going to be paid $30 for working 20 hours. Okay, now when I test, what I should have already done ahead of time was think, well, for this test data, the output should have been 200. But now I see that the output is 30, so I have a logic error. I have a logical error, and hopefully I see that, oops, I should have multiplied here instead. Okay. When the output comes to be 30, and I know the output should have been 200, I have a logic error. And the logic error is in this false part here. So you find that error and you correct it. You rerun it. It will now be 200. Output will be 200, which is what I expected.